Right, they don't happen all that often. So, why would something that doesn't happen often support a research belief? This is the crux idea right here. Why would something that doesn't happen often support a research belief? Back it up to concrete terms. We're trying to show that caffeine lowers heart rate during submax exercise, right? That's what we're trying to show. We're trying to show caffeine lowers heart rate during submax exercise. That's what we're trying to show, okay? Why would an outlier help us show that? Why would an outlier or a rare event or something that doesn't happen very often help us show that? Jamie, go ahead.
Well, if your test is along the lines of the null, the huge, then that outlier is going to say this is not the huge.
Because we're basing the test off the null curve or the null hypothesis that caffeine is not lowering heart rate. And if it's not lowering, that means it's
Staying the same or raising.
nice. It's either staying the same or raising. So this curve represents the sampling distributions. If caffeine is either staying the same, i.e. within a couple standard deviations, or raising. But where did our data fall? It fell over here somewhere. It fell in this lowest 5% of the curve. In other words, it fell outside of the what? Use a term from last exam.
Margin of error.
It fell outside your margins of error for the 95% confidence interval. Are you seeing the tie-in between confidence and that 5%? 95. It's a little bit goofy. This is a one-sided 95% confidence interval. We've always done two-sided in class so far. But because we're trying to show that caffeine lowered, instead of having the 95% confidence interval here, I took all the area that was blank over here, chopped off some over here, and shoved it over there. So in other words, you know how I usually go -2 to 2? It's not quite down to negative, it's like more like -1.6, because I had to shove it that way to fill up that tail. It operates, don't pollute your mind with that worrying about that though. It operates under the same assumption. It's outside the margin of error for the belief that caffeine is not lowering heart rate. Bob, I love what you said. It falls outside the margin of error of acceptance for that. Which means, I love what you said, it's not huge. Usual would be caffeine either kept heart rate the same or raised it. But we landed down here. Michael?
So that 5% is essentially predicated on your null hypothesis at that point.
Exactly. It's showing you that there is less than a 5% chance that we should have gotten data this extreme, assuming that it should have been over here. It should have been somewhere in this curve. It shows complete disagreement with the huge belief that caffeine is not lowering heart rate and the fact that we got data that said it is. That's a contradiction. We're believing caffeine's not lowering the heart rate. Holy crap, caffeine lowered heart rate. So you've got sample data versus a universal belief, and they're not agreeing with each other. Could we be wrong? Of course, this curve has outliers on it, on this side too. It could very well not be lowering heart rate, and we got some deviant data. This is why it's so important to check your data, make sure you didn't inadvertently somehow confound the variable with some other measure. But the chance of being wrong is pretty small. There's a much better belief, and we'll get into that with the green tea and breast cancer rates. So that's why small p-values imply yay for research hypotheses. Why don't large p-values? We'll come back to that in a second. Here's a formal statement of it. We got lowered heart rate. This is the next slide. We got lowered heart rate data, assuming caffeine had no effect. Does that agree with this? It does not. What implies that there's disagreement? That guy right there. Disagreement, small probability. We're expecting this, and we got essentially the opposite. That's indicated by a small probability. In other words, we're in that tail of that curve. How do we get out there? That's an outlier. If it's an outlier, then it shouldn't be in that curve in the first place. Ish, basically. That's the basis of Math 244. It was a caffeinated perf, I apologize. All right, let's focus on not submaximal exercise, but the at-rest and maximal exercise. Now, we're making the same assumption for all three of these groups. We're making the assumption that caffeine either keeps heart rate the same or raises it. Now, what happened at rest or during maximal exercise? Look down where those blue lashes are. They fell exactly where you expected them to fall. Now, in these research articles, you'll notice you don't get this curve. You get this statement. You get this statement. What your brain has to process is, when you see a p-value bigger than 5%, that means you're, well, Bob,
In the margin.
within your margin of error of what you were expecting. You also won't see this in a research article. Okay? Oops. You won't see this statement. We were expecting caffeine to have no lowering effect on heart rate at rest. And guess what? We didn't get any lowered heart rate at rest. Is that a disagreement?
No.
That's agreement. We weren't expecting lowered heart rate, and we didn't get lowered heart rate. So again, you're not going to see that statement in the article. But what are you going to see in the article? The fact that there's more than 5% agreement. I know 5% doesn't seem like much. These p-values are often much larger than 5%, but 5% is this cutoff that's used, and we'll come back to why that's so important to use, so why it's important, why it's prevalent as we go through this course. So you're not going to see that graph. You're not going to see this statement. All you're going to see is what's up here, or conversely down here. That's what you're going to see. But your brain, make this connection right now. This is the big takeaway, and we're going to keep revisiting this all day long today. When you see p-values less than 5%, what happened? Your data fell outside of the expected margin of error. When you see p-values bigger than 5%, they fell, nice, insignificant or inconclusive, they fell inside the margin of error. Susie, ask me that question.
Oh, I was just going to say, is that also your 95% confidence?
That's exactly, let's go back to the graph. Yes. This right here, this green or gray, whatever color this is, that is your 95% confidence interval. So when you fall within it, you're greater than 5% on a p-value. The only way to fall outside is to be in that last 5%. Oh, in that last 5%, that means less than 5%, because you're outside that margin of error. Fair enough? Think of it, can you think of an analogy between falling in and falling out of the margin of error and the fish tanks? Can you think of an analogy? How they're tied together? When the tanks overlap, when the confidence intervals overlap, when the tanks overlap, would you be a green dot or would you be a red dot?
Green.
I have votes for green. Are we okay with green? Got a bunch of agreement there? Good. That's exactly correct, isn't it? Because, Karen, you just said inconclusive or insignificant. You said one or, they're both correct. When the tanks overlap, there's no significant difference between the tanks, because there's always a possibility the parameters are either lower than or greater than or the same. So you can't tell the difference. Just like when the asterisk is in the confidence interval here. Nothing's changed. Nothing's different than what you were expecting. But when you pull outside of that confidence interval like you did for submax exercise, what happens to the tanks? Now there is a tank over here in the red area, and there's a big green tank right here. And can the fishies in the big green tank get down to the red tank? No, nor vice versa. So what you're really looking at is two tanks. When the tanks are overlapping, there's nothing to keep you from believing there's only one tank. Basically, essentially. But when they're two separate tanks, they're two separate tanks. And that, Susie, go ahead. It becomes significant versus insignificant. Very nice. Ish? Ish getting there? Good. I want to keep this idea going. This is the, we're setting the stage for the rest of the course right here. And this is why I created this section. This section doesn't exist in any stat textbook, which bums me out, because seeing you guys as you're like slowly starting to put together the connection between confidence intervals in this usually takes place in half a page in a traditional stat textbook. That blows me away. First of all, nobody reads that half a page because it's in the chapter. And secondly, it's a half a page. It's a half a page. Holy hell. How many of you have read research journals before? Research journals before? A couple of you, a few of you. Most of the rest of you will at some point. So interpreting the results is almost, I dare say, maybe even more important than running the tests yourself. Being able to read a research, a psych journal, a human development journal, an ECE journal, a natural resource journal, and go like, man, maybe I should be dumping raw rat feces on my garden. This report says I got better corn growth, raw rat feces, and maybe some mercury too for my thermometers. Look at the results of this. And then you look at it, you're like, holy hell, no, it doesn't say that. It's exactly the opposite of that. Keep the rats out of your garden. Susie, go ahead.
I was going to say, you didn't ask how many of us understood.
Oh, we're working on the understanding. You're right, we're working on the understanding. That's the whole point. And those of you that did read the research journal, and you're like, okay, I see a P. That's a pretty common letter. But now we're working on the understanding of what that big P means. Very good. Thank you. Proving my point, Susan. Proving my point. Okay. Let's get caught back up here. So here, I don't think we got this far last time. But essentially, this is a synopsis of everything you guys just said 100% correctly. It's the next slide on your page. So when you get a big P value, Karen, the beautiful word you used was big P values.
Oh, insignificant.
Insignificant results. Inconclusive is a more commonly used result, a more commonly used phrase. When you get big P values, inconclusive results. In other words, what you're trying to show with Darla's research hypothesis has not been supported with your data. And that's because the null belief has been supported with your data. And when the null belief has been supported, you haven't escaped the confidence interval. You haven't escaped the margin of error. Which means nothing out of the usual happened. Nothing out of the ordinary happened. What do I have down here? Large p-values imply the two pieces of your conditional probability. What word would you put in there? So here's, good, I like that. I like that word. So we got our non-lowered heart rate data. So we got data in our sample. Heart rate wasn't lowered. Assuming that we weren't assuming it was going to be lowered. Because we said caffeine's not going to lower it. So what does this piece do with this piece? I like the overlap. I was thinking for a less mathematical, more English word, but overlap's perfect, Barry, just so you know. Correlate. Good. That's a good one. Correlate's a good one. Any other words? I was going to say agree. Is that okay if I say agree? That's the one that pops to my mind. The data in the sample agrees with what you were expecting to happen in the population. But I love overlap. Love that. I love correlate. Whoever said correlate was great too. All these words mean the same thing. It means what you were expecting to happen, happened. But remember, what you're expecting to happen is the opposite of what you're trying to show is going on, right? So if what you're expecting to happen happens, it's almost the opposite of what you want to happen as a researcher. Is that fair? Go ahead, Michael.
So the real trick in this is honestly to ask the right question.
Well, or take the right measurement. Michael has hit upon something very important over here. When you run research studies, you're going to notice there are two distinct kinds. There are the kinds that result from surveys and counting, and there are the kind that results from measurement. Counting constantly gets harped on in statistics journals because the right question or bias in questioning, as you saw from your first project, the bias in questioning can actually do a really good job of undermining what you're trying to study. Whereas a properly taken measurement cannot. Did anybody doubt my Del Taco half-pound bean and cheese burrito data? Probably not, because I used a ridiculously precise scale to measure them. It's like, okay, he was good. Wait, was it a Fender amp or a Marshall amp that you measured those things on? Like, I mean, you're not gonna get upset with how I did that. But if I come up to you and go, Jared, so I got a question for you. Do you agree with the direction that the U.S. is taking? Or are we plunging headfirst into a quagmire of cesspool of irrationality and Christianlessness? Right? I mean, think about that. Think about how I just phrased that. Now, compare that to what Lou Dobbs said on his show, and it's not that far off. That guy's got a talk show and more money than we have altogether. But he asks questions like that, and people take it seriously. Sorry, Lou. Nah. But that's the point. That's observational studies like that are much better than self-selected response studies. So yes, hold that thought.
But there are some that have been studied that are those that.
Just hold that, Michael, hold that thought. What you're doing is you're getting very refined in your questioning, and I love that. I'm trying to keep a big picture for today. No, I love what you're saying, and we got 5 weeks to explore that, and I hope we do.
Okay.
Yeah, actually, I don't hope. I know we will. Jamie, go.
So if we're getting, or if they were getting, a really high probability of lowered caffeine, then we would be thinking that we had the right idea when we had the wrong idea the whole time?
Good. What Jamie is pointing on, we're going to explore this in great depth. Suppose, can I back up a couple slides to the previous graph? Okay. Here, let's use this again. So suppose, this goes back to your heart rate Viagra, whatever it was, cholesterol drug Viagra example from last. So suppose we've got this null curve set up. Right?
Let me know for something.
And it ties in beautiful with Jamie's saying right now. So we're expecting to fall down here. If we fall in here, what we've shown is caffeine does not significantly lower heart rate. Now, if you fall here or here, you're well within 2 standard deviations of where average heart rate should be on caffeine, right? What if you land way out here? Now, you still cannot support that caffeine lowers heart rate. But what you may have inadvertently just shown, not only does caffeine not significantly lower heart rate, it raises it ridiculously significantly. So you might actually get exactly the opposite of what you're trying to show. So in other words, you discover something else by accident. Go ahead, Gene.
That's actually not what I meant.
Damn it!
I know.
That's what I heard you say.
But, great.
That was only going to answer to a question you didn't ask.
I know, well, I'm confusing, I guess, but
That's
what
okay.
I mean to say
Let's
is
go back.
like, if you found with not only some submaximal, but at rest and,
If they were all significant,
if they all lowered heart rate, then we would have been thinking that, generally speaking, that caffeine raises, your heart rate,
Mhm.
it actually, we had the wrong idea the whole time.
at least with respect to exercise.
Right.
Right? Now remember, this is a very, very specific research question. Is it raising or lowering heart rate with respect to exercise in elite male cyclists?
So I guess what I'm saying is
Mhm.
when everybody's an outlier.
Good, then you have the wrong population. But remember what everybody, this is why defining your variables is so important. Remember who everybody is.
Those 9 guys.
Right, well, at least the population represented by those 9 guys. Those 9 guys are in a very, very small population, elite male cyclists, probably of the same age, I would imagine, too. So yeah, you're right. This is why we have things like polio vaccines. Because we have this belief that, well, the polio just down swimming pools, basically. That's the null belief. No, the research belief is we're wrong about that. If you get this injection, we're down here now with polio rates versus up here. So you're right. I mean, this is where statistics does the world a favor. By finding those alternate populations, our original beliefs may or may not be true. If we can repeatedly support that they're not true, that's called replication of a study, and we start seeing the right population, we're honing in on where the truth actually is.
So what happens then if like, everybody's having lower heart rate at all?
Define everybody.
I mean,
Right.
all the 9 guys, all your sample.
Well, then you retest it with 9 other guys or 12 other
You
guys.
have to retest.
Replicate. Right. Remember, friends. Remember, we're at 95% confidence here, right? Which means there's a 5% chance we're wrong. So this could be an outlier study. In other words, Jamie, my friend, hang on, let me back up again. I think I got your question now. 95% confidence interval. 95%. There's your margin of error. Margin of error. 95%. We could land out in this tail, even though we're supposed to be here, because this thing has a tail, right? It has a tail, but you'll see after the break, it's more likely that you're not in that tail. It's more likely you're somewhere else. Is that fair? Good. Great question. Great question. Speaking of break, you got that glazed look. Michael, we're going to start with your question when you get back. That's cool. Is that cool?
Yeah.
Can we do that? Let's start with Mike's question. We're going to revisit this, and we're going to move on to the green tea. But let's take 5, because you're getting that look.